Hello, everybody, welcome to another edition of WAVY Science Lab. I'm meteorologist Jeremy Wheeler, and we are here today talking about the sun. We're going to be talking about all kinds of fun things about that hot ball of gas in the sky. You can learn a few things today, and I'm your host again, meteorologist Jeremy Wheeler. It is great to be here with you on this day. So, the sun, there's a lot to talk about with this. We're going to talk about some of the details. We could go into so much detail in so many different directions, but we're just going to kind of do the basics today and maybe talk a little bit about how it affects us. So let's talk about it. And the sun is going to, we'll start off with this presentation. All right. Sorry, I got a little flustered. So the sun is out there, and it affects everything we do, right? The weather, the climate, space, everything. It's got some impact in our lives. And so the sun, throughout human history, many have worshiped the sun. Many billions of people have worshiped the sun, millions, billions. Egypt, they had the sun god Ra. Norse god was Sol. Greek, Helios. The Hindu is Surya. And some of these I knew, some of these I didn't. Incan was Inti, I believe, and in Persian was Mithra, and hopefully I pronounced those correctly. But some of those are very ancient, so especially the Incan one. I'd never heard of that one. So, there's various rituals through time. Some of them archaic, some of them a little more modern even. And there's still some groups which worship the sun, and they're out there. Hello, Mr. Sun. Let's take a look at the graphics here, and there. All right. So what we're going to do is we're going to talk about these the various building structure. We're not going to talk about them, but we're just going to mention that they're in there. So let's talk about some of these. So Stonehenge, they believe it was built to kind of go with certain solar events, right? Through things like, the solstices part there. That's what I was looking for. The solstices. And so the pyramids were also built. Some of them, they believe, and coincide with certain solar events as well. Solstices and time of year, and then Temple of Apollo. Placement and structure evolved around some of these solar events. In Mexico, right, there's certain pyramids. There was one, I believe, that the steps line up at certain times, and it looks like a spine of a dragon or a snake, I think, the way it's lined up with certain events. Really cool how they did that, how they knew to do that throughout history. All right, so the sun is about 4.5 billion years old, and it's a glowing ball of hydrogen and helium at the center of the solar system. So it's this ball of basically explosions over and over again, and gravity's pulling it in because there's so much mass. There's gravity and it's pulling in, but at the same time, these explosions, these reactions are trying to push out. So there's a balance there, and it's in a good balance, especially the sun. It's 93 million miles from Earth. That's pretty far away. 150 million kilometers. That's very far, but it takes that light doesn't take that long to reach Earth. So the sun is 100 times wider than the Earth, and that's give or take. I think I looked it up, and I think it's technically 109. I think they rounded down. This is from NASA, so I think they were kind of just doing common speak. So give or take about 100 times wider than Earth, about 10 times wider than Jupiter, and the diameter is about 865,000 miles across. Think about that. That's huge. 1.4 million kilometers for those that want to know. And so its gravity holds the solar system together too, because the planets are attracted to that, and they're going around. Otherwise, the forces would push them off. They would fly out into space, but they're rotating around that sun. So let's break it down a little bit more. What is a star? And so a star is a giant ball of hot gas, mostly hydrogen and helium. And it is constant reactions going over and over again. It starts as a loud cloud of gas. Gravity causes these clumps of gas to start to coalesce and come together, and then eventually, the process of them compressing creates heat, and so there's more heat, more pressure due to friction, and so it just keeps increasing over and over again. Here's a good example. This is the Carina Nebula, courtesy of NASA, and so it's a giant cloud of gas, millions of miles wide, And so in that this is where stars are born, these clouds of gas usually. And so they start coming together and they heat up. And then once you get that reaction to happen, then you can get a star to form. So after millions of years, immense pressure and temperatures in the core squeeze the nuclei of the hydrogen and the atoms together. And then once they start fusing together, you get fusion, nuclear fusion, then you get helium to form. And that releases energy, right? When you do that, that's, the physical process of squeezing them together is so much that they physically, fuse together, and then that releases that energy. And so these heat explosions, again, I mentioned, balanced by gravity. So here is a picture of the sun, and we can take these now. You can't just go out and take a picture of the sun. I guess you can with your camera, but you got to be careful. But now we've got telescopes, we have instruments to be able to do this, satellites, and so again, this is courtesy of the sun, courtesy of NASA rather. And it's beautiful. It's just a beautiful object. It's too bad we can't see it like this on a day-to-day because it's just so beautiful, and you can see all the reactions there and all that, all that's going on. So here's the structure of the sun, and there's so many different parts to it. You got the core, radiative zone. You've got the convection zone, and then just all these different parts of chromosphere. So let's talk about that a little bit. The core, right? The central region where the nuclear reactions change from hydrogen to helium. And that's the middle, very dense. And then you got the radiative zone outside of that, extends from the core to the convection zone, radiates out that energy through the process, right? And then the hot gas, the plasma, in the convection zone, it rises and falls and it mixes in there. That's the outermost layer, the sun's interior part. And that plasma, it rises and sinks. So then the photosphere, and I'll back it up a little bit. So the photosphere is the layer that you can see, right? That's kind of almost a skin layer, if you will. And so that's the photosphere. So that is the visible surface of the sun. And the chromosphere then is the irregular layer above the photosphere. That's where the temperature rises from 6,000 to 20,000 degrees Celsius. That's hot stuff right there. Of course, the whole sun is hot, but different parts are hotter than others, and some much more. Then you got the transition region. That's the thin, irregular layer that separates the corona from the chromosphere. And we're going to talk a lot about the corona here in just a little bit. So maybe we'll take a break here at this time, and we'll kind of let that gel a little bit and come back and talk about the chromosphere. All right, we'll be right back. All right, we are back, and we're talking about the sun. We just talked about the different parts of the sun, and it's all hot stuff, but some parts hotter than others. Talked about the size a little bit ago, and kind of interesting fact. So if the Earth were a size of a basketball, then the sun in relation would be about 100-foot diameter ball. It'd be that big, about 107 feet. So that's kind of interesting stuff. All right, so now let's go back into the layers of the sun. So we talked about the corona just a little bit. The corona, not the beer, sun's outer atmosphere, region of hot, low density plasma. That's kind of important because this is the filaments that are away from the sun. And so the thing is, it's 2 to 3 million degrees Fahrenheit, but that's away from the outer shell. So the farther you get away from the photosphere, it creeps up from 10,000 degrees Fahrenheit up to 2 to 3 million degrees Fahrenheit. So how is that possible? Well, basically, it's the magnetism makes these particles accelerate and go even faster, and that releases all this heat. So there's a lot of high temperature, but there's not as much mass. So we talked about heat versus temperature in another podcast, and so this is a good example of that. I mean, yeah, it's 2 to 3 million degrees Fahrenheit, but there's not as much mass. So is it as much heat? Well, it's hard to tell, but they do go out and measure it. Now, let's talk about the sunspots because, and first off, let me show you a picture. So the corona are those thin filaments, as you get away from the sun, and you can see that when you have an eclipse, right? And that's when you can see the corona, but usually you can't see it. It's very faint because it's very thin. All right, so you get these sunspots on there, and you can see it, but let's take a look at the wider version here. And so these sunspots, I mean, they're dark. It's really neat. I mean, this is an actual image from NASA. And so those sunspots, it's a region of cooler temperatures. So what's happening is you've got these cooler regions caused by the magnetic field lines, basically. And so these areas of high magnetism, it disrupts things in the the photosphere, and so and below that, the chromosphere. So the temperature in the sunspot, 6,000 degrees versus 10,000, in the regular photosphere, and that's where you can see them, But it happens below that photosphere. But I mean, still, that's where we can visibly see them, and so it makes a cooler region. But interestingly, because it's a cooler region, yes, but that occurs when there's more activity. So when you have more sunspots, you have more solar output, and usually it gets, it's hotter from the sun's output. So these things have been tracked for hundreds of years, and people thought it was Galileo that started, but there was someone before him. But I just didn't commit that to the presentation today. But I mean, since about that time, sunspots have been tracked, and even longer than that, even. But just more formally, I think, since the Renaissance. Anyway, lower amount of sunspots will be during cooler periods of climate, right? Because there's less solar activity. So the trend is interesting because it's going down while global temperatures are increasing. So you get these aurora in there. Let me show it to you. So there's aurora borealis, right? We get the high activity from the sun and the solar wind. And so then you get these particles, these high energy particles up in the atmosphere. And so when that happens, then you can get those aurora to form. So solar cycle 25, and there's a whole bunch of cycles. We're already, kind of coming out of the maximum, and it goes up and down, right? These cycles, of course, by definition. So these solar cycles, 25, the maximum is passed. I think we're still in solar cycle 25. And you can kind of see it right there. Just that there's on the top, there's the curve that kind of just slowly goes up and goes down. That's a breakout of this other chart on the bottom. And so, again, it's going to peak, I think, or go down rather, 2030. I think we're going to get down to the minimum again. But right now we're coming out of the maximum. And there's been a lot of aurora. We had a lot of, northern lights the last couple of years. And so that's because of the activity. And there you can see the different cycles that go back to, I believe, the 1800s. I can put my glasses on, but I think it's 1800s. Let me put it on anyway. Let's see. Yeah, there it is. Yeah, I think so. Yeah. So, and that's, when they've been kind of more formally tracked. Okay, so that's the sun cycle. Now, there was a Maunder minimum, is what they call it, in the 1600s. And so that was a time when the temperature of the planet dropped, a little bit. And so, the temperatures and the climate were directly tied together for a long time. The Maunder minimum was a good example. Was it the Dark Ages, I believe, and maybe the tail end of that, and then going into the Renaissance. So it was a cooler period in Europe especially, but I think over in probably the United States, well, before it existed as well, in North America before that existed. So then, and you can see the cycles. Another period in there, 1800s, early 1800s, 1816, I think, was the year without a summer. Now, there was also a big volcano that year, so that, but I think the combination between those two, there was hardly a summer at all. I think in July they still had frost or something like that in the United States. It was a weird year, and crops were lost, and it was a tough year. So, but that's another time. Anyway, so that's one. Now here's kind of looking at the solar radiance versus temperature. And that's been, tracked, I think, for quite some time. But I think using the solar cycles and the sunspots activity, I think that's how they did it back to the 1800s, because they didn't have, the satellites they have now to measure that type of thing. But yeah, the temperature going up, but the sun activity kind of going down there up until 2020. All right, so here's some size comparisons. Our sun, one solar mass. Red Giant is huge, right? It's so much bigger than that. And this is the end of a kind of a normal size star like our star. It goes to Red Giant. And so then there's a lot more to talk about with this. I could have a whole podcast probably on the end of star's life, which I may do that. But then it after a time, it just grows and it becomes less dense. It loses mass, and then eventually it gets back down to a white dwarf. You get the red dwarf there, but a white dwarf is about the same, I think. So that's much lower mass. And then you've got a blue supergiant or a white supergiant, 150 solar masses. Those are huge. Those end in a supernova, right? Because they have so much energy in there. And so those usually tend to explode. And so, we've got the different sizes. Pretty neat to see. And this is process is going to happen to billions of years, not just anytime soon, anything like that. So we got a long time. But just think about that. I mean, our sun is so much bigger than the Earth, and then to see these others that are so much bigger. Matter of fact, a red giant will consume a couple planets. I believe at least Mercury, maybe Venus. This is from old memory, but I don't remember if it would consume the Earth directly, but it would just heat up because it would get so much closer and bigger. The Earth would heat up. So that'll be happening in billions of years. All right. So we're going to come back in a little bit, talk a little bit more about the sun on Earth and some effects from it and some activities that happen revolving around the sun. We'll be right back. Welcome back. Well, you thought I was going to be wearing some sunglasses, but I didn't. I decided to wear the regular glasses and make myself the super nerd here. So here, I got your glasses right here. All right, I'm back. That's my alter ego cam. In case you didn't know that, so that's I pull that out to just have a little bit of fun, kind of the Jon Stewart idea. But anyway, maybe it works, maybe it doesn't. I don't know. You're out there laughing or saying, "I can't believe this guy. He's so terrible." Anyway, hopefully you're not saying that. All right, so now let's go into a few other things like the sun, how it affects the Earth. And sunlight coming in, we got the different seasons, and so throughout the year the Earth is tilted 23.5 degrees, so throughout the year the sun angle changes for us too. Now we're looking at the different angles. I don't know if this is for everybody. I think this is at our angle, at our latitude, so because meteorologist Don Slater put this together a while back. But anyway, in June, 77 degrees. In December, 31 degrees above the horizon. So that's a big difference in the sun angle. And that makes a huge difference in how much of that sun is, hitting the Earth, or how strongly it is, I should say also. So you got the different angles, and that sun comes in. It's composed of, radio waves, microwaves, infrared, visible light, of course, X-rays, gamma rays. It's got all this radiation in there, especially UV rays. Now a lot of it gets filtered out through the atmosphere. A lot of it gets filtered out through the atmosphere, but some of it makes it through. And, the ozone layer blocks those high-powered UV rays. So the infrared radiation comes in. That's a part of the spectrum that's the heat, and then light gets converted over to heat too. It gets absorbed and changes over. So that's what heats up the planet. And then you've got the greenhouse effect, which the heat gets trapped into the atmosphere, which is a good thing. We want to have some of that, right? Because otherwise the heat would escape all into space and we wouldn't be able to use it. So but when you have the lower angles, you have less infrared. And so during the wintertime here in Hampton Roads, well, we have cooler temperatures and in our latitude. So observing the sun, there's many instruments used to observe and measure the sun. You've got on the ground a pyranometer, I believe, measures the sunlight. That's from the National Weather Service, and it can tell you how much sunlight in a day. And then space, you've got the Solar Dynamics Observatory, the Solar Orbiter, the Parker Solar Probe. And that's interesting because that's very recent. That got closest to the sun ever, I believe, and so it passed by the sun at 3.8 million miles. And you think, wow, that's pretty far away, isn't it? But I mean, relatively speaking, that is very close. And at top speed, it was moving at 430,000 miles per hour, 119 miles per second. Think about how far 119 miles is to you and me. Just driving it would take forever, a long time anyway. But yeah, I mean, per second. So then it got close and it measured the sun at that, and it took all these different readings and measurements. We learned a lot from it. I think it's pretty recent, so I think all the information going to get processed, and then they'll come with us, and give us all the results and stuff. But it's still in the process, I believe. So that's the Parker probe. All right, so then we've got the sun hitting us every day, and you've got the UV index. It's courtesy of the Environmental Protection Agency, and So you get up into the higher numbers there, and you got to put that sunscreen on. You get very high, 8 to 10, 11 is extreme, low is 2. I'd say 3. I kind of lump 3 and 4 into low myself, just kind of using my chart, I guess. And then you've got all these different bins in here. The explanation to it, the breakdown. So when you get it into the high and very high, you need to do that sunscreen, especially I say 50 or higher. When you get it higher or very high, you want to have that sunscreen SPF 50. And just, think about this. It's kind of embedded in there, but you've got white sand or very light colored sand or white home. It's reflecting that light, or snow. So you get that extra light. Now, when it snows, it's usually colder, but you can get, extra light to hit you from above from the sun and below from the reflection. And so that can help cause sunburn a little bit more so. And so you get a UV index today. It's a 6 when I was recording this, which is, I'd say moderate to high, not super high. All right. And then going back in time a little bit, talking about an eclipse that we had in 2024. So that was April 8, 2024. Very cool. And so some folks traveled to go see the totality when, the whole sun was blocked. And in that image there, you can see the corona. Very cool. I mean, there's plenty of pictures out there, but I mean, that's a good example of it. And then, that was over the Midwest. And again, I'll mention over and over again, this happened in the past. This happened in 2024. But it was very cool to be around that. And then we had one a few years before that, too. So, I know meteorologist Jeff Edmondson, meteorologist Ricky Matthews traveled to go see it, and the path of totality. We had a pretty good show here, though, in Hampton Roads. We had about 78% blocked by the moon, and you had to have those special glasses, or you could have a special telescope, but it's got to block out so much of the light, and welder's goggles, things like that. But because that light, you can't look at the sun directly anyway. It's too hard when the sun's out. But then when it's blocked, well, it's less light, and you think, okay, well, I'll be safe. But no, it's not. And plus, some of that gets kind of enhanced around the edge of that, and so you can get eye damage from looking at that. You really can. All right, so and that's back again when it happened, and the dates and information. Then you got the lunar eclipse, which can happen, and that's the opposite, right? So one is the sun in between the Earth between the moon, and then the other is the moon in between the Earth. And so in this case, you can see the lunar eclipse happens, and you've got that shadow of the Earth. And so when the moon gets around that, it gets into the kind of the reddish light there, the umbra from a total eclipse. And then that's, you can kind of see that reddish color when it gets over there. And pretty neat when that happens. So you get those dark red moons when you get a total lunar eclipse. All right, so that is a lot about the sun today. Let's do the last part, and that is the environmental tip of the day. Just want to mention, seek out sustainable seafood. Lots of folks eat seafood, especially around here in this region. So fish, shellfish, and seafood that's caught or farmed in a way that allows production and habits to flourish. And you can go to fisheries.noaa.gov and topic sustainable seafood and learn a whole bunch about it. Just want to kind of mention it, that it's out there. Keep it on your radar, pun intended, and it helps out the environment. All right, so that's it for today for the sun. Hope you had some fun, and everybody have a good day. Thanks for watching.